Today we'll introduce the concept of flux, which we will need soon to discuss some very important behaviors of electric and magnetic fields. To start, we're going to develop an analogy with the flow of a fluid. So imagine we have a container that holds some fluid, say water, and we cut a hole in the container like this. Now we're not showing the entire container here. We're zoomed in and focusing only on that part of the container wall where the hole is. The hole has area delta A. And let's imagine the instant we cut the hole, water starts to flow out with a velocity vector v. Let's assume, for simplicity, that the velocity is uniform over the entire hole. Now, if we wait for some time delta t after we cut the hole, some volume of water will have gushed out. We can calculate that volume, which has a base area of delta A and height v delta t, where v is the speed, the magnitude of the flow velocity. The volume of this fluid is then just delta A times v delta t. Now, the rate at which the volume of fluid is gushing out, the volume flow rate, is the volume divided by delta t, or v times delta A. Now, in doing this calculation, we assume that the velocity was perpendicular to the whole area delta A. Now imagine we cut a hole in a different container. And when we do this, we see that the water just flows past the hole, like this. That is, the velocity is parallel to the area of the hole. In this case, we would have a very different volume flow rate. It would be 0. More generally, if we imagine that the velocity makes some kind of angle, like this, then when we are calculating the velocity flow rate, the only component of the velocity that matters is the component perpendicular to the hole. We can make this notion of perpendicular to the hole more rigorous by associating with the area delta A a unit vector n hat, that is normal, meaning perpendicular to the surface area delta A. Then that part of the velocity that we care about for computing the volume flow rate would be the component that lies along n hat. That is, the volume flow rate would then be v cosine theta times delta A. We can write this as the scalar product of vector v and n hat times delta A. Again, we're assuming here that the velocity is uniform over the area delta A. We're going to use these same math operations now to introduce the concept of flux for some vector E defined on the surface area delta A. The quantity vector E dot n hat times delta A is called the flux. We often use the Greek letter capital phi to represent the flux. Let me emphasize here that the concept of flowing is not needed here. What is essential is that we have a vector field, here vector E, defined on some surface, here delta A. Those are the key ingredients for computing the flux of vector E on the surface delta A. Now, given this choice of the letter E, you might guess that this is how we define the electric flux, the flux of the electric field on the surface delta A. This definition assumes vector E is uniform on delta A. Similarly, we can define the flux of the magnetic field on the surface delta A. This is how that's done. Again, we assume that vector B is uniform on the area delta A. Let's try working this problem involving the concept of electric flux. What is the electric flux on this disc-shaped surface? Stop the lecture and try to work the problem out before continuing. Since vector E is uniform on the disc-shaped surface, we can use this expression to find the flux. Here is the expression for the area of the disk, delta A. This arrow represents n hat. And notice the relevant angle for the dot product is this angle, 90 degrees minus theta. So here's how to work out that dot product in terms of theta. We plug in all the numbers and we obtain this result. Now, if the electric flux is not uniform over a surface, this can happen if vector E or n hat or both change over some surface. Then here's what we need to do. We need to pass over to the limit of small areas dA. Each such infinitesimal area will still have its own normal unit vector, so the differential d flux E is given by this expression. To get the total electric flux over the entire surface, we'd need to sum up all these small contributions of d flux E by integrating. It's the same story for the magnetic flux if it's non-uniform over some surface. We need to keep this in mind for the future. Finally, let me make a comment that's relevant for other courses that you might take. As we discussed, here is how we define a volume flow rate in terms of the flow velocity vector V. But this is not by convention called the volume flux. In cases where there is transport, flow of something like volume or mass, the corresponding flux is defined differently as a rate per unit area. So you may want to keep that in mind. That's it for this lecture. We'll use this concept of flux extensively beginning in our next lecture, where we introduce a very important idea in electromagnetism, Faraday's law.